Happy?
Happy.
Yeah? Good. So, welcome.
Hi.
We're going to do your physics right here today, and we're going to talk about electricity.
Mm-hmm.
So, can we start off? Can you tell me what is current?
Current is the flow of electrical charge through a conductor. It is measured, the base unit of current is the ampere, and 1 ampere is equivalent to the flow of 1 coulomb charge per second.
And what symbol do we usually use to denote current?
The symbol commonly used is I.
Perfect, yeah, absolutely. And so what different types of current do you know of?
There is alternating current, AC, and direct current, DC. Direct current, the flow of current is in one direction. In alternating current, the direction of the flow of current alternates periodically or reverses periodically.
And so what is voltage?
Voltage is the term used to describe electrical potential energy. 1 volt is equivalent to to 1 joule of energy being dissipated over that's wrong.
That's great. And what is the voltage value of mains electricity? Can you tell me a little bit about that?
So the voltage value of mains electricity is 240 volts.
Okay.
That is the root mean square value of voltage, because the mains electricity is alternating current. Therefore, the voltage varies across the current cycle, meaning that the positive and negative values would cancel out.
Mm-hmm.
So by squaring each value throughout the cycle and finding the mean of that value means that you get rid of the negative values.
Yes, absolutely. Brilliant. So 240 volts, root mean square. And then how about resistance? So what is resistance?
Resistance is the opposition to to current flow in direct current in a conductor.
So how do voltage, current and resistance relate to one another?
So Ohm's law describes the relationship between voltage, current and resistance. So Ohm's law equals V voltage equals current times resistance. So the electrical potential energy is proportional to the flow of current times the resistance to flow.
Yeah. What is the equivalent of resistance in alternating current circuits?
The equivalent to resistance in alternating current is impedance. Yeah.
That's great. So what about power? What is power?
Power is the rate of dissipation of energy.
Perfect.
So is joules per second, and the unit is watts.
Perfect, yeah. Do you know any equations for power?
So one equation for power is Q equals I times V, so current times voltage.
That's great. So tell me about electrocution. What is electrocution?
Electrocution is occurs with the passage of electrical current through the tissues of the body, usually causing damage to the tissues, and occurs when a body completes a circuit.
Mm-hmm.
Therefore, the person has to be touching the circuit at 2 points. Typically occurs at currents of 100 milliamps.
So what sort of factors will will influence the effects of current flow through the body?
There are several factors that contribute to the severity of effects of electric shock. So firstly, the type of current, the frequency of the current, the amount of current. Then there's also the current density and the duration of the flow of the current.
Anything else that you think might have an impact, particularly with relation to microshock?
The pathway.
Yeah, pathways, really. That's great. So I just mentioned microshock. Can you tell me what microshock is?
Microshock is occurs when current is applied to the myocardium, causing ventricular fibrillation, and it occurs at currents of 50 to 100 microamps.
So how does that compare? What sort of non-macro shock, what sort of macro shock currents would produce what sort of effects? Do you know of any values that would be relevant?
So with AC mains current at 50 hertz, the 1 milliamp is the current enough to cause a sensation, so tingling. 5 milliamps causes pain, and is the maximum safe current. 8 milliamps can cause burns. 15 milliamps causes a tonic muscle contraction and the can't let go phenomenon. 15 milliamps can cause respiratory arrest and severe burns, and then 100 milliamps can cause ventricular fibrillation.
Okay. And so what measures do we take here to reduce the risk of damage from electricity?
There are several measures used in theatre. So there are general measures. Such as maintenance and correct appropriate use of equipment, and the staff wearing appropriate footwear that has high impedance. There's also the use of floating circuits which isolate the patient from mains electricity and there's no earth connection. There's also use of earth nothing current, in addition to circuit breakers and equipotentiality, which is the ensuring that the voltage of two currents in close proximity are equal, therefore reducing the risk of current flowing between them.
Can you tell me a little bit more about the classification of electric equipment for medical usage? Do you know the classification system?
Yes, so electrical equipment is classified either according to its degree of protection or by its minimum leakage current. Minimum leakage current. So a degree of protection, the classification is the classes. So class 1, 2 and 3. Class 1 doesn't have a symbol, but it has an earth wire that is connected to any conducting parts that are accessible to the user. Thereby, if a fault occurs, then it will travel down the earth wire as opposed to through the user. Class 2 is double insulated, so all electrical parts have a double insulation again, and no earth is required. And class 3 is uses safety extra low voltage, which is for AC is 24 volts and DC is 50 volts, and usually has its own internal power supply or a battery, or is isolated from the main circuit by a step-down transformer. And then the classification by minimum leakage current is the type classification, so type B, type BF, and type CF. That's not a person, that's a person in a box, and that's a heart in a box. So type B, the minimum leakage current is less than, it's 100 microamps. And it's safe for connection to this body surface, but isn't safe for connection to the myocardium. Type BF again is 100 microamps. It's safer than type B. Can't remember why.
What does the F stand for?
Floating. It's floating circuit. But it again can't be connected to the myocardium. Not safe for use, cardiac use. And then type CF is safe for cardiac use and is used for central venous catheters and pacemakers, and has a leakage current of 10 microamps.
That's great. Perfect. Well done. Yeah,
That was really impressive.
really good.
Well done, Kat. That was really good.
So like that's
The detail is hairy.
that's a clear part, isn't it? I mean that's a clear too. So
Hopefully.
no, it is just is. There's no way there's anything on the past there. So that's brilliant. And I think there's a couple of things there that I've got slightly different values for, but even that stuff doesn't really make much difference. I think they'll give you parts and stuff like that. So yeah, brilliant. Well done.
Thank you.
Really good. And it's not like that. You picked a tough one for yourself. You picked a tough one for yourself.
Hopefully now I know it.
I thought you go for flow. I really did.
Flow.
I thought you go for flow. That's what I would have gone for.
Yeah.
Flow was like nice and easy.
Thank
No, awesome. Well done.
you.
Yeah. But was there anything in there that was particularly worth picking up on? I don't think there is massively. So the respiratory paralysis and burns, I have a 6 amps, which is a massive current. I think you said it was 50 milliamps, so I think it's quite a big disparity there. VF is 100 to 300 milliamps that I have here, again, so a bit higher than we said. The other thing is I think these values are for direct current, not AC. I think you said it was AC.
Right. Yeah, because there's different, I didn't want the context of various different resources show different amounts, and it's like, but what is that relevant to? Like, what's the actual?
And they're often not specific, and there's quite a lot of errors in the kind of the classic physics textbook that I think everyone uses as well. I noticed a couple of fairly substantial errors in there of core values that can be asked on. So you're not going to get too tripped up by specific values and truths as long as you have a conceptual understanding overall. I think it's quite a difficult thing to test in practice, isn't it?
So big, this is going to sound so stupid, big A is amp, normal MA is milliamp, which is 100th of an amp, and like funny M, A is a microamp.
Exactly, yeah.
And I think I get the two M's mixed up. So with the B, BF, and CF, that's talk that those leakages are in micro, aren't they? Yeah.
Microshock is micro.
Yes. Yeah. Okay.
Yeah, you're absolutely right, and that's what the physics textbook that I've got wrong.
Yeah.
You put an M in front of it, it said milliamps, and I was like,
It's
I'm pretty sure that's not true.
Yeah.
I've seen that typo before as well. It's a bit of a bad one, isn't
It's
it?
a really bad
It's a
one.
really bad one.
It's 100 times out.
And then
so.
the article I was reading didn't use the universally accepted symbol for micro. So what we're talking about here is the SI units of prefixes, aren't we?
Yeah.
Which is actually something that is in a few of the mock stations, which is just thinking about your milli, micro, kilograms, as opposed, and you use exactly the same prefixes for amps. But yeah, they used a proportional to symbol in the article, which completely threw me. So they used, instead of this, which is your normal micro symbol, isn't it?
Yeah.
They used this.
What? What?
Well, exactly, which is completely off for me.
That means proportional to.
Yeah.
Exactly. Yeah. Or alternatively, it's the alpha symbol.
Yeah.
Yeah.
Well,
Either way, it's not right. And that was in an article written by none other than Steve Pumphrey. So,
Wow, okay.
Yeah, really, really well done, mate. That was good.
Yeah.
Great. We've got some practice questions. Should we do some of those quickly? And I will also quickly just flag up a couple of resources at the end as well, because I don't know if you guys have come across them, but let's do screen first. That sounds...
Well, you had the power. Yeah, the power. There's like different.
There are, yeah. So that is a derivative of the, I can't remember, it's V over R.
It's I squared R.
I squared R.
Substitute for
But P equals IV is one as well. Isn't
Yeah, and then exactly, I squared R is the derivative. You put Ohm's law into power is equal to VR, and you get I squared R over that somehow through clever mathematics. Good. Should we do some questions? Yeah. Well done, Gavin. Not easy standing up in front of
Yeah,
everyone.
it was really good.
yeah, really well done.
And all three of you are now going to be working towards Viva, aren't you? Good. Same invitation goes to you as gone to the other guys, which is if you want to have a chance to
Yeah.
do the being Viva thing, it's a chance to practice and to study
I don't want to.
No,
Which I should do.
It's
good.
You know what? I'll take 4.
Character building.
I'll take character building. Great. So
Now I'm going to get in the MCQs wrong.
it's fine. You don't need to know
Don't
anymore.
need to know anymore,
In fact,
yeah.
none of you do. I don't know why I'm bothering.
Hang on, this is best of 5.
So this is multiple true false questions. So each one is either true or false. Tick
Oh,
ones
so you take it
tick
true.
ones you think are true. I just need to start writing some SPAs. They're just much harder to write.
Yeah. Got some stuff really.
It's terrifying, isn't it? It's absolutely terrifying how quickly it goes.
Yeah. Because there's a thermistor, and I need to not get confused with thermistor and a resistor.
Good. All right, we've got 3. That'll do. So I reckon those ones are true. So should we talk through them? So first one, resistance of a wire is directly proportional to its length. So this I've put in there as not as a, well, because it does come up in the temperature questions, and you might be able to draw those graphs relating resistance to temperature for. This comes down to the difference between conductors and semiconductors. Can anyone tell me the difference between a conductor and a semiconductor?
And so a conductor will always allow the passage of electrons along it.
Yeah.
Semiconductor only does under certain conditions.
Yeah.
Like when it's heated up. Or
Yeah, exactly. Yeah, so this is to do with how currents pass through them. So current is transferred by having 3 electrons buzzing around, right? In a conductor, you've always got 3 electrons buzzing around. So you always get a flow of current through them. But actually, as temperature increases, the activity of those electrons increases, they buzz around a lot more, and they essentially provide resistance to flow by getting in the way. Think of it conceptually. Whether that's true in physics terms or not, I have no idea. So I think about it. They're moving around, they're getting in the way. It's like people nipping in and out of shops on Oxford Street, you can't walk past them.
Yeah.
Right? With a semiconductor, you have to heat it up to get electrons out of what's called the baseline band is called up into the valence, so out of the valence band into the conduction band. So you have to give the electrons energy to free them in order for them to be able to pass current at all. So this is, remember, states matter and energy. So if you've got, put it in a pen, that'll help. So conceptually, this is your material, and you've got the valence band, and then this is a higher energy state. And in order to get your electrons from this band into this band, you have to add energy. So they will only conduct when you've added energy to it, i.e. heat. So the resistance in a semiconductor is going to decrease as temperature increases because you're increasing the number of electrons available to carry charge. Whereas in your conductor, the electrons are just buzzing around more and more excitedly and not doing what they need to do to conduct the charge around it, which is why resistance increases in your resistance by thermometer and decreases in the thermostat, which is the semiconductor or metal oxide. Isn't it? So actually this is your fundamental basis of why those temperature graphs are the way they are. And actually this is sort of a penny drop moment I'd be thinking about it backwards. Understand the difference between a conductor and a semiconductor, and those graphs will make sense when you get outside temperature.
So the true statement would be, in conductors, resistance is generally proportional to temperature.
The resistance of a wire is directly proportional to its length. Yes.
Okay, sorry,
yeah.
I was looking at all of this.
We were doing the temperature one as well.
Yeah.
Yeah. So yes, it's directly proportional to temperature, not inversely proportional to temperature. The resistance of a wire is directly proportional to its length. That's true. So this is just exactly, you can, again, this is another big error, I think, in the physics book. The physics book said that resistance is lower in thinner wires. And I've looked that up online and I think that's not true. I think you can apply all the same concepts of Poiseuille's law to electrical current. But that's just me questioning something that's written in the textbook. So just take that statement with a little bit of caution. Resistors in series, so connecting resistors in series. So what are resistors in series?
When they're like next to each other rather than on different like branches.
Yeah, that's something I wouldn't be able to explain, but I could draw a thing.
Yeah.
Okay, so these are three resistors, they're connected in series, right? And then you've got three resistors in parallel.
It's 1 over, isn't it?
Yeah, you times their inverses, I think. So for the resistors in series, you have R1 plus R2 plus R total. So that's your resistors in series. And your resistors in parallel, you add the inverses. Is that right?
Yeah.
That looks right to me.
And it's the same for compliance in trust rules.
Exactly, compliance is resistance in its own way, isn't it? It's a measure of resistance. Okay. So series is they're connected sequentially, aren't they? Whereas these are all connected at the same point, but just in parallel to one another. Great. Direct contact with the live component is required to cause an electric shock. I think that's false. Coming on to why? Just going to jump. Okay, yeah. So you have sparks, static, that sort of thing. Any other reasons why that's false?
Because you might touch the wire which is connected to a live component, and then you'll then be the so you're not technically directly touching it, but you're touching its current.
So the other thing I'm getting at here is capacitive coupling.
Okay.
So can anyone tell me what capacitive coupling is? Or how floating circuits work, or how step-up, step-down transformers work?
So the floating circuit is where you have basically a transformer, don't you? And you have equal windings on one side and the other, so you can't get.
So how the current flow across that if it's not touching?
It's to do with does it induce a magnetic field which causes the sort of electrons in the other coil to move in the same ways.
So it only works with alternating current. And this is because we come back to the basic physics concept that any moving current induces a magnetic field, and any moving magnetic field induces a current. Right? So if you have a moving magnetic current, like you do an alternating current, because we're moving back and forth, you start to create a magnetic field around it. And that shifting magnetic field, so if you have that on this wire, it creates a magnetic field here that's always shifting, and if you hold another wire in that magnetic field, it'll induce a charge in the other wire. And that's how you have floating currents. That's how current flows without direct contact from this one to this one.
And that's the same as capacitive.
So that is capacitive coupling. That's how you can end up with an alternating current in the wire and a person having a capacitive current induced in them by that wire. It's also how floating transformers work and how there's a risk of electric shock to patients if they're connected to earth, even if they're not directly connected to the line or wire.
Because they'll get induced, they'll have a.
If you induce a current and there's a risk that
it will
current to go through the
earth.
patient to earth, then there's a risk of shock.
And they both have to be connected to earth, don't they? So yeah, they're
Pass.
both.
I think the
For
patient
it
has to
to
be connected
create
to
a
earth.
circuit.
I'm not sure if the other current does. I'm not sure. That makes some sense. So we've done that one, we've done wire resistors, done light component, done conductors. Current is the flow of electrical charge from the positive to the negative terminal.
Electrons go from.
Electrons go from negative, current goes from positive. It's
That says
annoying.
electrical charge. Charge is the flow of electrons.
The flow of the electrical charge, the
Current is.
electrical current, yeah, maybe I should phrase that.
yeah.
So electrical current flows from positive to negative. I may have written that question wrong between myself. I'm just trying to emphasise the point that current flows
Current
positive
and
to negative, and the electrons flow from negative to positive. Think that's enough?
Why does current flow from positive to negative?
Because that's what they first did before they understood what electrons were. So they just
Historical.
took it as a convention that then
Okay.
subsequently discovered subatomic components and electrons
Mm.
and realised they actually flew in the opposite direction to what we thought. By that point, everyone had
Okay.
created positive and negative terminals, and the entire world worked on that
I see.
premise. So
Yeah,
it was too much
okay.
effort to undo it. Not just to trip up primary candidates. I
Yeah.
promise. I'll be interested to see if this is controversial. Cool.
Yeah.
Sorry, guys.
No.
I thought this would be controversial. Fine, good. So should we go from the top one? Earthing of medical equipment.
That creates a circuit or a passage through which any current can flow. So ideally you want isolated circuits.
Exactly. So actually, the safer scale of circuits in the class class 1, 2, 3 system are actually the ones that are not connected to Earth. So Earth is both a safety feature, but it also increases the risk of electric shock in some situations. So that's probably a bad thing. Use of safety at low voltage equipment.
You can still get micro shock
Exactly.
if there's degradation of the
Yeah. So the
pipe.
safety at low voltage equipment can still produce a sufficient current for a micro shock if it's connected in close proximity. So the key thing here is the class 3 equipment. This is a general classification of equipment, not a medical specific classification, which is why we have the type B, C classifications, because that's directly for medical equipment. Because even the highest protected class 3 equipment is not suitable for things like central venous wires, pacemakers, that sort of thing. Okay. Use of CF equipment is the one that protects you against microshock. It's got the heart in the symbol, so that's C for cardiac. Class 2 equipment isn't even the most protected standard classification of equipment, so it's probably not right. And mains electricity cycling at 50 hertz. It's the worst, isn't it? Yeah, absolutely. So,
How do you interpret this? So if you have a grey bar,
so grey, it's both whether you have, if it's negative, so if it's not a correct answer and you haven't ticked it, you've got it right, if that makes sense. A double negative is a positive.
okay. So if it's just grey, then
That means it was an incorrect answer, but if you didn't select it and it's grey, then you got it right.
Yeah,
Makes
okay.
sense. It's not marking you, it's telling you which answers are right.
Yeah, and if I've ticked something that's
Grey.
wrong, then you get a red.
Oh, fine, yeah, I think.
Yeah.
And if you ticked it and it's right, you get green.
I'll be honest with you, I haven't done a whole lot from your end, I'm really sorry.
The circles, the little circles with the cross or the tick, is whether you have got it right or wrong, and the grey or red, I think, is whether it's. Oh no, never mind.
Because
It's all very.
I've got
False.
ones that are just grey.
Yeah.
So all the grey ones are false.
There's only one true one there, which is the CF equipment. So if you tick any others.
Okay, so I think basically if I've left it unticked and it's right, then it just leaves it grey.
Or or you could just look on that.
Okay,
I think
yeah,
that's
sorry.
Sorry, mate, this may not be the best use of this piece of software.
No, it's
Good. One last one. Great. Okay. So regarding the UK main supply, the mean voltage is 0 volts. So, and the peak voltage is 240 volts. No one thought that was true, so that's good. The mean voltage is 0 volts. Let's quickly talk about the AC thing again, shall we? So you might be asked to draw the AC/DC currents, and it is pretty straightforward to draw, to make sure you get the axes and the units right. So this will be your AC graph, right? And so put volts, but you could easily have current on the y-axis, and obviously put time on the x-axis. You want to make it a sufficiently long scale of time, so you can have to have milliseconds. Because what is the frequency of mains electricity?
50 hertz.
50 hertz, which is how many cycles per second? 50 cycles per second. So each cycle is 0.11-ish millisecond seconds, isn't it? 0.01-ish, something like that. And the point being here that each time, so if you take the mean of all these points, it's obviously going to end up equaling 0, isn't it? The mean of all these points. If you took the average of every point of the graph, it'll run through the middle of it, which is 0. Because every time there's a point up here, it's counterbalanced by a point down here. Every point up here is counterbalanced by a point down here. Every point up here is counterbalanced by a point down here. So they cancel each other out, which is why we do the root mean square. So Catherine's explanation of it was perfect. What you do is you take each value on this, you square it. So the square of -2 is 4, isn't it? Because the square of any negative value becomes positive. So you end up then with a graph that looks a little bit more like this. Okay. And then if you take the mean of all of that and square root the mean, that gives you the root mean square voltage. So you take the mean, because then you've all got all positive values. Take the mean of all the positive values and then just take the square root of that mean and take you back to the root mean square voltage. So the UK main supply has a root mean square voltage value of about 240 volts. And you can do the calculations if you're very keen, but essentially that means that the peak voltage is around about 340 volts. It's 339.7, I think. But the peak voltage is therefore not 240 volts.
Yeah.
If you're asked to draw DC, that's the easiest thing in the world to draw. It's this. Yeah. That's quite straightforward.
How many volts?
Well, it depends what battery are you describing it from. So you use it with a 5-volt battery. Nice and easy. Because that's your standard little one, isn't it? You get asked to draw, well, you won't get asked to draw anything, but. So rectifiers are used to convert DC to AC current to power certain appliances. I think this is false. Can anyone tell me why?
I got it wrong. It's the other way around.
It is unfortunately the other way around. What is used to convert DC to AC?
Alternators.
An inverter, I think.
Okay.
Yeah, so a rectifier takes, so basically cycles at the same rate as your alternating current and flips the poles. So basically what you end up with instead of that is this. Just a bouncing positive current like that. So it just flips every one of the negatives up to the positive. And an inverter does exactly the opposite. So it'll take your AC current in and periodically flip the poles, flip the direction of current. So you end up with a current that looks a little bit like this. So it becomes alternating. So periodically inverting the current.
That's because it's a diode as well, isn't it? Is that
I may well have something to do with diode, and you're getting well beyond what I can remember from the electricity books. I'm not sorry,
sorry?
Good. So we've done mean voltage, rectifiers. Okay, electricity is conducted in overhead power lines at a lower current than in the domestic power supply. I think that's true. And tell me why. Yeah. Yeah. Exactly.
But I thought it was low resistance, which means it's efficient resistance.
No, so the resistance is constant, isn't it? So the resistance is a property of the wire. So if the resistance is, so you've got your three variables, right? Or, so if you make the resistance is, if the resistance is constant, then therefore V is proportional to I, isn't it? Sorry,
If it's high
one
voltage,
over I.
it's high current.
Yeah, it's inverted proportional to I. So if you have higher voltages, so first law of thermodynamics is conservation of energy, right? So you have energy that you're creating, and you're changing one form of energy, i.e. the potential energy, and you're increasing that. So you've got to get that from somewhere. So it's got to be taken from the current. That goes from the kinetic energy, if you like. So it's higher voltage and lower current. And do you know why they do this? Why they use a high voltage, low current and get it through the wires? Why? No, so this is, so thermal loss is power, isn't it? Energy dissipation against time. And we just said that power is equal to I squared times R. And if your resistance is fixed, then the greatest determinant of your energy loss through power, which is something that energy companies want to minimize, is your current. It's the square of the current. So if you reduce your current, you reduce your power loss quite drastically. Obviously, you can reduce your power loss by reducing the resistance, but these are long wires, aren't they? We just said that resistance of a wire increases with increasing length. So you can't really change that. You've got to transport energy over a long distance. So the best way to save energy is to reduce your current and increase your voltage. That's just trying to make the power equation a bit more relevant.
Does the resistance increase in the long, because it's a long power line?
So the resistance of the wire as a whole is increased because the wire is long. It doesn't mean that as distance along the line increases, the resistance only increases. It's a whole wire thing, because the resistance is taken as between 2 points, isn't it? So the beginning and the end of the wire. So the resistance is continuous, but it's just bigger than it would be for a shorter wire.
Could you, so just going back to V equals IR?
Yeah.
It's not, why is it 1 over I?
So if you have,
Why is it inversely proportional rather than proportional?
so
The one going up and one going down
Yeah.
makes complete sense, but from that point.
mathematically,
Sorry, I'm just-
So we're saying that resistance is going to stay constant, aren't we? So we're going to say that resistance is constant, so therefore it is V divided by I, so therefore they're inversely proportional. That's the way to think about it. So for a fixed resistance, you're making the resistance constant, so you want to put the resistance on this side of the equation. In order to do that, you have to divide the voltage by the current. I got them in and I didn't need the numbers.
Yeah.
Sorry. For a given resistance, the two other values must be inversely proportional. Yeah. Cool. You made sense, but I couldn't tell you why. Got there now. Good. Last one. The neutral wire is connected to earth at the substation. That is true. So this is important to know for electrical safety reasons, and I honestly can't tell you I fully understand why. But it is important to know that your standard electric circuits, like your 3-pin plug socket for your lamp, is connected to earth at 2 points. So you have your power station, which transmits energy in the wires, and then it gets a step-down transformer at the substation. So this is like your big power station. That gets step-down transformer, so your voltage gets stepped down to your standard 240 volt meter square from the however many thousand volts it is in the power lines. And at that point, you have 2 wires. You have the live going out, and you have the returning neutral. The returning neutral connects to earth there. Back in the house, which that's the house, you also have the 3rd wire, which is the neutral in the house as well. Okay, but the neutral is maintained as neutral by being connected to a substation.
There's 2 neutrals.
There's 2 neutrals. Essentially. One in the house and one back at the substation as step-down transformer.
And then the appliance itself hasn't had.
It may do, depending on the class of electrical equipment it is.
Oh, okay.
If it is class, so the majority of stuff we use, like that light box and all there, will have
Yeah.
a neutral because it's a 3-pin plug socket.
Okay.
Sorry, an earth.
Yeah.
Neutral.
Okay.
Yeah. Eventually, it'll make sense to me why that's important, but it has come up in some practice questions. Good. Sorry, electricity really pushes me.
Yeah, I hate it.
That's pretty much all I know about electricity. Yeah, that's probably plenty, isn't it, to be honest?